Today we're going to be going over rational functions and points of discontinuity. We're going to talk about rational functions first, where p of x is over q of x. And I'm going to highlight that so you can see what I'm talking about. And both p of x and q of x are going to be polynomials. And polynomials are like what's stated right here on the right hand side. Q of x is equal to a binomial, 2 terms, divided by a trinomial, which is 3 terms. So what we're really getting into is that we're going to be dealing with these types of rational functions, and they're either going to be continuous or discontinuous, and we're really going to focus on discontinuous today. Continuous would be you can graph the whole entire graph without lifting your pencil off the page, and that's really, really important to see, versus discontinuous, which means you'd have to lift your pencil off in specific spots. So for asymptotes or holes, which is our next point. Points of discontinuity are places where the graph is discontinuous. This is represented with asymptotes and holes. So to find these points of discontinuity, we are going to determine which x values will make the denominator 0. And this is really important to see here. So we're going to look for points of discontinuity. You can see on our first problem, we are going to look at the denominator. There's nothing to reduce on top and bottom, and that's going to leave us with x will be equal to 5 is a point of discontinuity. The second problem, we're going to have to factor both top and bottom, so let's do that. I have a difference of squares on the top, so this is going to be x minus 5 times x plus 5, and on the bottom, what multiplies to be 15, but subtracts to be 2 is going to be x minus 5 times x plus 3. You can see right here we will have a reducible function, but we are only looking for points of discontinuity. So let's take a look. X minus 5 is equal to 0 and x plus 3 is equal to 0. This is what we're doing. We're looking to see which denominator values will equal 0. Well, again, x is equal to 5 and x is equal to negative 3. Our last function right here, this is going to be another difference of squares, so x minus 6 divided by x plus 6 all over x minus 6. This, again, will come into this talk in just a minute. You can see that this is actually reducible, but we will have a point of discontinuity at x is equal to 6 because we're setting x minus 6 equal to 0. But remember, again, what would make the denominator 0? That's going to be our points of discontinuity. So here are some rules for vertical asymptotes and holes. If a rational function has a 0 in both the numerator and denominator, then that it means it's a hole. Okay, so the way that I remember this is it's reducible but not forgotten. So reducible but not forgotten. That is what a hole is. If a rational function has a 0 in the denominator that is not a 0 in the numerator, then it is a vertical asymptote, not reducible. So let's go back up. Example 2 says, hey, which ones are going to be holes or asymptotes? Number 1, this one right here is not reducible. So this one is going to be a vertical asymptote. So vertical asymptote. And from here on out, I'm going to label these as VA. Now, on number 2, x minus 5s will cancel out. That means at x equals 5, that is a hole. This is a hole at x equals 5. The other one does not cancel out, so this x plus 3, or x equals negative 3, that must be a vertical asymptote at x equals negative 3. For problem number 3, we have x minus 6's canceling out on both top and bottom, leaving us with a line, y is equal to x plus 6. But we can't forget, remember, reducible but not forgotten, that there is a hole at x equals to 6. And so when we draw this line, here's 6 right here, once we draw this line, there's a hole here at 6. So we're going to do the second part of 8.3, which is talking about not only x-intercepts and y-intercepts and horizontal asymptotes, but we're also going to throw in what we just discussed, which is vertical asymptotes and holes. But we got to talk about our rules of horizontal asymptotes. So we're going to kind of Tarantino this. We're going to start off with the third subject, which is horizontal asymptotes, or end, and then we're going to come back through and we're going to do some x and y intercepts. But going from other math classes like Algebra 1 and Geometry, we should know how to find x and y intercepts. We'll talk about that. If the degree in the numerator, so that means the power of your variable, is greater than the degree in the denominator, there is no horizontal asymptote. Okay, so an example of that is x squared plus 6 divided by x. This is going to have no horizontal asymptote. Now, our next rule is if the degree in the numerator is equal to the degree in the denominator, then we have to look at a horizontal asymptote of a over b, where a and b are our leading coefficients. So let's take a look at number 2 here. We have an x squared on both top and bottom, and a is how many x squareds I have on top, and b is how many x squareds I have on bottom. So we'll have, in this situation, a horizontal asymptote at y is equal to 1 over 1, which means we just have a horizontal asymptote at y equals 1. Well, we did number 2. That's good. If the degree is the degree of the numerator is less than the degree of the denominator, then a horizontal asymptote is always y equals 0. So this one is defaulted. An equation like that would be x over x squared minus 4, something similar to that. So let's look at number 1. Well, these are the same degree. If they are the same degree, then we have y equals a over b. In this case, we only have 1x over 1x, so y is equal to 1. That's where our horizontal asymptote is at. We're just looking at what's in front of our x's. For number 3, looking at that, we have more, or there's the degree is greater on the top than it is on the bottom. So in this case, there is no horizontal asymptote because degree or top is greater than the bottom. So top is greater than bottom. And this is just what we're dealing with powers. So this one is really, really important. Make sure you're taking a look at these notes and pausing, maybe reading through it a couple more times. We're going to flip back and forth from this. But example 2 is finding holes and finding asymptotes. So this is just your this is you cataloging what's on the graph. So there is a hole at x is equal to -5. Oh, we have an x-intercept here, x-int at x equals -3. That's going to play into part later. Oh, hey, look, I have a vertical asymptote at x equals -2, and another vertical asymptote at x equals +4. There's a horizontal asymptote at y equals 0. That plays into a big key role right here. That means right here our horizontal asymptotes at y equals 0. So we have to play this game now. We know that there's going to be more x's on the bottom. In this case, we have 2 vertical asymptotes on bottom and a hole. Remember, holes we have to cancel out, so there's going to be one on top and one on bottom. But there is a vertical asymptote at x equals -2. So the opposite of that is +2, so x plus 2. Then we have a vertical asymptote at x equals 4, which is x minus 4. And then we have a hole at x equals -5, which is going to be a +5. And that one has to happen on both top and bottom because we will reduce that when we process this. Now our last clue is kind of our look into the future. Again, Tarantinoing this. X-intercepts at x equals -3. Well, we find our x-intercepts because they're on the numerator, and we're going to be setting those equal to 0. So this one's really x plus 3. Again, we have a degree of 2 on top, and a degree of 3 because there's 1, 2, 3 x's on the bottom. So it follows our rule. And you can check this in Desmos if you really wanted to. Y is equal to this, and you can look at it. I don't want you to multiply it out. I just want you to put it into Desmos just like it is right here and see if it matches, which it does. Now, our last component here that we have to learn or relearn is finding x and y intercepts. To find a y-intercept, we make x equals 0, and then we solve for y. So in this case, we really just get rid of our x's and then just find the number. Okay. For x-intercepts, when we're talking about these graphs here, we need to make sure that we are working with zeros for our y and solving for our x only after we found our holes and vertical asymptotes. So again, for this one, we want to set y equal to 0 and then solve for x. So let's find our x and y intercepts and our holes and our vertical asymptotes in this function here. To find our y-intercepts, we need to just get rid of our x's or set them equal to 0, which is going to be -2 over -4, which in this case is going to be positive 1/2. So when we put in 0, we get out 1/2. That is our y-intercept. We need to find our holes. There are none because it's not reducible. There's no holes, not available. But there is a vertical asymptote at x equals 4 because we set our denominator equal to 0. Last but not least, we need to set y equal to 0 for our x-intercepts. But if you notice, what's going to happen here is we are just going to be getting rid of our denominator, because if we multiplied both sides by x minus 4, there is no more denominator, and we just have our numerator. So the rule that I like to remember is we just need to set our numerators equal to 0. So in this case, we have an x-intercept at 2, and we get out 0 for y. So we found all the things. Our last step here is to put it all together. We are going to work on one example. It's y equals x plus 5 divided by x squared plus 3x minus 10. And we are going to find y-intercept, the holes, the vertical asymptote, the x-intercepts, the horizontal asymptotes, and we're going to sketch it all. So again, to find y-intercept, we're just going to get rid of our x's or set our x's to 0. We end up with y is equal to negative or positive 5 over negative 10, and in this case that's negative 1/2. So when I put in 0, you get negative 1/2. So we're going to go down 1/2. We're going to look for holes now, and the only way to do that is to factor out the problem. We need x plus 5 divided by x plus 5 times x minus 2. And you can see that we are going to reduce the x plus 5, so we do have a hole at x equals negative 5. Now when we do reduce this, we end up with y is equal to 1 over x minus 2. So we're going to look for vertical asymptotes by setting our denominator equal to 0, and we end up with, in this situation, x is equal to 2. So that's our vertical asymptote, and we can put that on our graph. And then you'll notice that our last rule that we just discussed was set your numerators equal to 0. Well, to find an x-intercept, 1 does not equal 0, so there are no vertical asymptotes. There's none available. And then for a horizontal asymptote, if our power on top is less than the power on the bottom, because it's 1 over x, so if the degree in the numerator is less than the degree in the denominator, there's a horizontal asymptote at x is equal to 0. So there is a horizontal asymptote at y equals 0. That's just from the rules that were stated earlier. Now this is a single, so k value is 1 over x minus 2. We just moved our inverse variation to the right 2, essentially. So this is what the graph looks like, even with my terrible line. Let me fix that. And this is what we're working with. So there is one more example, but I would like you to try it. If you have any more questions, please feel free to reach out. Thank you.